Right, so we'll take one example, one complete example. Actually, I solved some more examples in notes, but I'll take only one example here, one full example. Okay, so the example is like design a bandwidth analog. Example is like this: design a bandwidth analog low pass filter whose pass band and stop band specifications are as follows. Okay, pass band attenuation alpha p. Pass band attenuation alpha p is given as minus 2 dB. Pass band edge frequency omega p is given as 2513.102 radians per second. Stop band attenuation alpha s is given as minus 20 dB, and stop band edge frequency omega s is given as 15506.08 radians per second. Okay, so they are asked to design a filter, design a band Butterworth. Okay, design a Butterworth analog LPF, analog low pass filter. Okay, so they're asking us to design a Butterworth low pass filter. The specifications are given. So the frequency responses are shown in the figure. The same frequency response is shown. Alpha p is the given, that is minus 2 dB. Alpha s is given as minus 20 dB. Passband edge frequency omega p is given. Omega s is given. Okay, right. Now what is the procedure to design this? So always remember, when there is a specifications given for a Butterworth filter design for any kind of filter, maybe low pass, maybe high pass, or whatever. Okay, so you know the edge frequencies, you know the values of alpha p, alpha s, omega p and omega s always, right? So the first step is always to determine the order n. Okay, so if to calculate the order of the filter, which is n, which you denote it as n. So we know that 3 dB cut of frequency omega c and of the required Butterworth filter. Okay, right. So we know the order calculation equation n. So n is given as log of 10 raised to minus 0.1 alpha p minus 1 divided by 10 raised to minus 0.1 alpha s by 1 whole divided by 2 into log omega p by omega s. We know this order n equation, right? We have derived this order n equation. So using this order n equation, I will calculate the order n. So you substitute all the values. You have all these data available with you, right? You have alpha p, you have omega p, you have omega s, you have alpha s, right? So if you substitute all these data, you get the n equation. So n, what you get, it is 1.4091. You can calculate and check. Okay, 1.4091. We also know that if n is not an integer, you have to round it off to the next higher integer. So it is 1.409. Then I'll select n as 2. So here my order of the filter is 2. Okay, now you calculate the omega c. So you have to do these two steps. First you have to calculate the order, and then you have to calculate the omega c cutoff frequency, right? So 3 dB cutoff frequency omega c. 3 dB cutoff frequency omega c is nothing but given as omega p divided by 10 raised to minus 0.1 alpha p. Okay, 10 raised to minus 0.1 alpha p minus 1 raised to 1 by 2n. So you know this data again. You know the omega p value. You know the omega p value, you know the alpha p value. So substitute it, you get the omega c cutoff frequency as 2873.414 radians per second will be your omega c, which is cutoff frequency of the filter, right? Now step 2 is, right, this is a step 1. Step 1 is, in step 1 again I have divided to, first you have to calculate the order and then calculate the omega c. So that is your step 1, to calculate order and omega c. So now the step 2 is derive the transfer function of the second order normalized Butterworth filter. Okay, or select the transfer function of normalized Butterworth filter if the table is provided. So either you can derive it or you can take it from the table depending on the availability. So if your table is given it, you have to directly select from the table, or you can derive the procedure is already explained to you, right? If order is 2, you have to consider there are 4 poles, 2 lie on the left half of S plane, 2 lie on the right of S plane. You calculate the angular separation between them, right? And then consider only the left of S plane and right its equivalent denominator terms, and finally you get the total transfer function. So here I'll directly select, which is already done. So h of s is equals to h2 of s is nothing but h2 of s is equals to 1 by s square plus root 2s plus 1, which is derived in the previous section. We'll directly take this. So now I know this is second order normalized Butterworth filter transfer function. So here now I apply step 3 is what, to apply analog to analog frequency transformation technique, right? And here I want to design a low pass filter only. Okay, so it is LP to LP transformation. I'll apply LP to LP transformation. So the equation is H of S equals to H2 of S, where S is replaced by S divided by omega C, and my omega C is here. How much I got the omega C? 2873.4 pi. So S is replaced by S divided by 2873.4 pi. So wherever there is a S in this transfer function, you replace this S by S divided by 2873.4 pi. So you write it in that way, 1 divided by S square divided by S is replaced by S divided by 28.734 pi. So this is S square here. So this becomes S square divided by 2873.45 whole square plus root 2 S. So S is again replaced by S divided by 2873.4 pi plus 1. So now you have to simplify this and take the LCMs, right, of the denominator, and then the complete, when you get the LCM of the complete denominator, that goes to numerator. So the numerator value is 2873.45 whole square, and whatever remains in the denominator you write it according to that. I mean mathematical, it's a mathematical simplification part. So you get 2873.45 whole square divided by square plus root 2 into 2873.453 yes, okay, and plus 2873.45 whole square. So this is how you get your transfer function of the required filter what you want to design. Okay, right. So this is one example which is designed for LP to LP transformation. Okay, there is one more example here which you can check. It is given in the notes. So design LPF to meet the following frequency response specification. The filter should have monotonic pass band and monotonic stop band frequency maximal pass band and monotonic stop band frequency response. Okay, the pass band gain is 0.9 and the pass band edge frequency is 2 radians per second. Stop band should be less than or equal to 0.52, okay, 0.2 for all the frequencies greater than or equal to 4.82 radians per second. So this is a data which is given, right? So you can calculate here they have given you the gain. Okay, so gain, if you take the attenuation part, it is again a negative out of it. So alpha p you calculate as this 10 log of 10 to 0.9, which is get 0.4 pi dB. Omega p you know 2 radians per second. Alpha s is again you have to calculate 10 log of, because you have to refer to this frequency response. They have given the gain, you have to take it attenuation of it, right? So you get 6.989 dB alpha s. So once you know all these alpha p and alpha s values, and you know the procedure already, right? You already done one example. Excuse me. Okay, so you know the procedure. Step 1 is what? Determine the order and omega c. So you know the equation for n and omega c. Substitute, you get the order and this thing. So once you get the order, get the transfer function of that order, normalized Butterworth filter order, right? And if you write that order here, so here you get the order as 3, you get the third order Butterworth filter equation transfer function, you write it, you replace this s by s divided by 2.89, okay, and simplify, you get the transfer function of required filter. Okay, right. So this is a design with respect to Butterworth filter, analog Butterworth filter design. Okay, so next we are going to see the Chebyshev filter design. Okay, and then we have to convert this analog filters to digital filters. Okay, actually we want to design a digital filter here. Okay, but directly we cannot design the digital filter. So first I design analog filter and then I will convert that to digital. Okay, so I can do here the digital filter part, but we'll go to the Chebyshev filter design and then convert that to digital filter. I'll understand how to convert those filters to digital filter. Okay, so these are just examples. We'll continue in the next video.